Okay, so for this module, we are kind of putting together the last piece of writing programs with conditional execution and learning how to control which branches actually execute. So up until now, we've seen relational operators been used as Boolean expressions. So our relational operators were less than, greater than, equal to. And we could write some branching statements based on our, using if statements based on those relational operators. But today, or with this module, we're looking at logical operators, which allow us to join together a series of Boolean expressions to create bigger and bigger or more complex decision structures. So these operators, we've actually talked about them very early in this set of modules. They're the and, or, and not operators that we heard about in terms of when we're talking about logic gates and the actual hardware. So not only does Boolean logic or logical operators come into play when designing hardware, but it also is going to find its way into our programs more often than not. So logical operators are covered in section 3.10 in the text, and they work fairly in a fairly straightforward fashion. We know that a Boolean operator can be anything that resolves to true or false. So a Boolean expression could be 3 less than 4. That's going to resolve to true. A Boolean expression could be, 8 is equal to 9, and of course that'll be false. That would resolve in false. Or it could just be a variable, right? It could be a Boolean variable that resolves to true, that of course is true or false. All of our logic operators are applied on Boolean expressions. And that's going to be important to remember. The left and right hand side of any one of these logical operators should always be a complete Boolean expression. The result of using these operators is another Boolean value, another true or false value. So the and operator, the or operator, and the not operator give us a pretty full range of ability to join together a series of Boolean expressions. And the symbols matter. There's no spaces between these two characters. We've got the vertical lines and the double ampersand. You want to make sure that you don't use a single ampersand or a single vertical line. That will mean something quite different. So normally when we talk about describing logical operators, we look at what are called truth tables. Really, it's just a table of what true and false values will come out of using these operations or these operators. So for an and operator, the double ampersand, if the left and right hand side are both true, so A and B are true, the result will end up being true. If either one or both of the left and right hand sides are false, then A and B resolves to or results in false. So for an A and B expression to be true, the Boolean expression represented by A and the Boolean expression represented by B must be true. For or, either one of them must be true. So for a Boolean or operation, either A or B or both of those expressions needs to be true in order for A or B to be true. The not operator simply takes a Boolean expression and flips it around. So any Boolean expression resulting in true, if you put an exclamation mark in front of it, it'll take on the value of false. So let's see a couple of examples before turning this into or turning over to a programming example. So let's say we've got a Boolean expression. I'm not going to use variables here. We'll just make them straightforward. 3 less than 3 less than let's say 4. So that Boolean expression we know, of course, resolves to true. Let's say, and we're going to put it in parentheses to make the precedence a little bit more clear. Let's say we've got 3 and 4 ampersand and then another Boolean expression. Let's say 8 equals 9, the double equal sign. Right, so this expression, of course, the 3 less than 4 will resolve to true. This is going to resolve to false. Right? And then if we look at the double equal sign or the double ampersand, true and false, that's going to result in a false. for this expression to be true, both sides must be false, or both sides must be true, excuse me. So let's try a couple other ones. Let's say we had 3 less than 4, or, and again I'll put the parentheses in there, we have something like 8 equals 9, and then an and I guess we'll do 11 is greater than 7. Okay, so first off, in terms of precedence, we're going to talk about precedence rules in a moment. Written as is, the and signs are going to take higher precedence over the or. So just like plus and minus are of a lower precedence order than multiplication and division in mathematical operators, in logical operators, the or sign is a lower precedence level than the and. So in this case, what we would do is we would take these two values and we'd evaluate them first. So this is going to be false. We have an and of course this is true. That resolves to false. Now we've got, and this of course is true, we've got true or this false. True or false will resolve to true because we only need one of the sides to be true in order for the result to be true. So the precedence is important. Now in this, if I had parentheses over here, something like that, then I would have done this part first. We would have still gotten the same answer in that case. We'll try out one that ends up being, I guess, false here. Let's say we've got 11 over 7, or 11 greater than 7, and we put a not sign. And let's say 3 less than 4. Okay, so the not operator actually takes the highest level precedence among the logical operators. This is going to be true. 11 is indeed greater than 7 with a not operator. And it's always a good idea to do what it's in the parentheses first to make it easier to come up with these Boolean expressions. 3 is certainly less than 4. Now this not operator is going to resolve to false. Now and true, and the result is false. So Boolean expressions can be constructed. Of course, any one of these variables any one of these numbers can be variables. Boolean expressions can be constructed using a number of different relational statements combined with these and symbols, these not symbols, and in the other examples, ors. And we can build up more complex decision trees using these type of operators. So let's look at a more practical example. Let's say that we are writing a program to allow a user to qualify for a particular loan. So for programming example 14, we're going to write a decision engine, so a very, very small set of decision rules as to whether or not you qualify for a particular loan, maybe a car loan. And we're going to assume that if you must earn over $60,000 a year, you'll get the loan, no matter what. The other condition is if you earn over $35,000 a year and you've worked at your current job for 5 years, then you will also get the loan. So there's two basic paths to get the loan, two criteria. So we're going to write a program that asks the user for their salary and how many years at their current job, and will output whether or not they qualify. So the conditions that they would not qualify for, of course, would be they've worked at the job for between or less than 5 years at any salary underneath $60,000. So before actually kind of going right to the code, I think it's a good idea to draw some flowcharts to think about how this logic might play out. And then we can see a couple of ways to take those flowcharts and really just shift them right into our C++ code. So we'll start with step 1 being read year at job and salary. Right? So that's our input. Step 2 is going to be really a decision. Okay, So is salary, and I'll put just sal, is it greater than 60? If yes, the user is approved. All right, we'll just put a check mark. If no, we've got another set of decisions. All right, is salary greater than 35 and years greater than 5? If that's yes, we're in. And if that's no, then we're going to reject the loan. So we've got a flow chart that's looking at a couple of different conditions. Now, without even thinking about our logical operators right now, we can take this flow chart and we can really just at each point in this decision build an if or else. And so let's start with that process, so kind of a mechanical process of doing that. And then we'll tie in our logical operators and we'll get our code to be much smaller actually. So we'll first start by coding up the input. Okay, so let's get our input. We've got years worked, and we'll use doubles for all of this. And salary. We'll ask the user. For our two inputs. Right, and if we flip back to our decision tree, the first thing that we're going to do is just say, is salary greater than 60,000? And if it is, then we're going to say you're approved. So if salary is greater than 60,000, see out, approved. All right, so I'll build that and we should test to make sure that works. Okay, so put 50,000 first. We shouldn't get any output. Oops, I actually need the years worked. No output with 50,000. And if we write 70,000, 5 years, we get some output that we've been approved. All right, so our decision tree, if yes, approved, else, no, else is going to be this part of our program. So when we deal with a flowchart without kind of optimizing our code at all, we can really just have an if and an else branch. And we'll later convert this into if else, and we'll use logical operators. So I'm just going to have an else branch. And inside that else branch, I'm going to literally write the next set of questions. If salary is greater than 35 and the years are greater than 5. So that's an and operation. Both of those criteria have to hold for the loan to be approved in this situation. So if salary is greater than 35,000 and years worked is greater and equal to 5, we're approved. Else, right, we're looking at this condition right here, else we're not approved. Okay, so we've got not probably the most elegant way to write the program just yet, but we've certainly got the program driven from the flowchart, right? We've got one set of decision, we've got one decision mechanism, salary greater than 60, you're approved. Otherwise, we're going to start to check the other clause, and we can either approve or deny. So let's run that and see if this is working with our input. I'll try $50,000 and now 5 years, and now we're approved. If I try $25,000 in 5 years, so that meets the year requirement but not the salary requirement of $35,000, loan is denied. If I have $80,000 salary and I've only worked for 1 year, I'm still approved. Anything over 60 would be approved no matter how long you work. And if I have, let's say, $45,000 salary and I've only worked at the job for 4 years, I'm denied. So I've checked all the different conditions here and I'm happy with it. Now once you've done that, once you've gotten to that point, you can look at the code and you can start to optimize. And there are things that we really actually do want to optimize. First, primarily, the fact that we're repeating this approved flag. That's generally not a great thing, to have the same printout statement resulting from two different parts of an if statement. So ideally, we'd like to collapse this all into one section. Now, the first thing that I can see before that, though, is that I have an else followed by another if clause. I really don't need to have it nested like this. That's what the else if clause is for. So I can refactor this code a bit to do the exact same thing, just in a little less indentation. Now, when I say exact same thing, you want to make sure that it does the exact same thing. It's called regression testing. When we make changes, when we try to pretty up our code, make it a little bit better, we definitely want to go back through our test cases and make sure that it still works. It's easy to make a mistake when you're refactoring that code, when you're improving the code, and have it not work. Right? So I'd go through all of the test cases. I'm not going to go through each one here, but under normal circumstances, I would go through all of my test cases again. And it's tedious, and eventually you'll learn the arts of writing automated testing someday, and you'll find it a lot less tedious, but it's important nonetheless. So now I see that I've got two if clauses, an if and an else if clause, that have different conditions, but the same exact result. So basically, if you say this out loud, if this is true, I write approved, or if this is true, I write approved. So why don't we turn that into C++ code that sounds like that. We can have our or operator joining together if salary is greater than 60 or salary is greater than 35 and years worked is greater or equal to 5. And remember, the AND operators have higher precedence, so this side will be evaluated completely first. Now I can get rid of this entire clause, and now I just have one area of my code that I actually print out, whether they're approved and denied, and I can change the text in one area, and it's not going to be different for different criteria. Right? So I started out with sort of something that comes right from the flow chart. Right? If I write a standard flow chart, I can crank out an if and an else statement. But then through the use of if-else and through the use of some logical operators, I was able to condense the code quite a bit. And so this would be the final product. Now, to summarize, we've actually seen most of the operators that we will see throughout the course. And there are a few more operators in C++ that you'll learn when the time comes. But these are the most common, and we've seen them all. The parentheses is actually considered the highest level of precedence, in that we always evaluate what's inside parentheses first, no matter what. I would recommend that you use parentheses liberally. We have these precedence rules in place that we're going to go through in a second now, but don't make a habit of testing the person who's reading your code's ability to come up with precedence rules. And what I mean by that is you should try to make your code as clear as possible, and the use of parentheses can very much help you with that. You don't want to write long, big long expressions that cause somebody to really think carefully about precedence rules to be able to understand what you're doing. But every once in a while you will see code that's written that way, and that's why it's very useful to understand exactly how these precedence rules work. So parentheses at the top, and then followed by the not operator for logical, and then negative, the negation operator for negative numbers. So those are always evaluated first after anything that's been done in parentheses. The multiplication, division, and modulus are of higher precedence than math. Importantly, the math operators themselves are of higher precedence than the relational operators. Moving forward, it would be a good idea to look at some of the problems in the textbook, in particular on this section. There's some case study problems, 311 and 312, that are particularly useful. There's also some written problems, or some expression-related problems in 3.21 through 31, which are asking you to solve some Boolean expressions. I'd highly encourage you to look through those on your own to get some practice. It's a good idea to get a lot of practice working with Boolean and relational operators. So when you start to work with them in programs, it's a lot easier. You've got a lot to worry about while you're programming. You want to get real good at logical operators as fast as possible. So for the lab for this set of modules, Lab 5, we're going to write a program that looks at how much money it would cost to ship something across a distance. So we imagine a shipping company determines how much it charges customers based on the weight of a package in a distance ship. The prices are determined by the following table. 2 kilograms and under is going to be one weight class, and then we've got 2 to 6, 6 to 10, 10 to 12, 20. So what you're going to do, your first step is really going to be to figure out what weight class the package ends up in. So you're going to ask the user for a weight. You're going to figure out what weight class is there, probably a set of if conditions, and that's going to drive the total rate, the amount of money per 500 miles that it's going to cost you. At that point, we would just make a straight calculation. So good idea to start with writing a little simple flowchart perhaps, or go right to the if conditions. What you want to look out for in this type of a problem is making sure that each one of your if conditions, or your clauses within the if and else's, only have what's different for those particular clauses. So if you end up writing 1, 2, 3, 4 times, if you end up writing the equation for weight times distance 4 times, or if you end up writing a cout statement to say the total cost is whatever 4 times, you have too much duplication in your code. So try to refactor that. It's okay to start out like that, but you want to try to avoid any duplication that you can.